For more than half a century, the global transition to renewable energy has rested primarily on the shoulders of one element: silicon. From the earliest space satellites to the sprawling, multi-gigawatt solar farms in the modern desert, crystalline silicon has been the undisputed king of photovoltaics. But silicon, despite its reliability and plummeting manufacturing costs, is bound by the unbreakable laws of physics. It has a hard ceiling, a maximum theoretical efficiency that no amount of engineering can bypass. Welcome back to Fun Facts Online. Today, we are exploring a staggering leap in materials science that just shattered that ceiling. To truly decarbonize the global economy and bring energy independence to space-constrained urban environments, the world needed a solar technology that could break the rules. Enter the perovskite-silicon tandem solar cell. In a monumental achievement, the solar industry recently breached the once mythical 34% efficiency barrier for photovoltaic conversion. Certified by the U.S. National Renewable Energy Laboratory, or NREL, a two-terminal crystalline silicon perovskite tandem solar cell developed by the solar technology giant LONGi recently achieved a world record conversion efficiency of 34.85%. To put this into perspective, the absolute maximum theoretical limit for a standard single-junction silicon solar cell is just 33.7%. By combining the traditional workhorse of silicon with the miraculous light-absorbing properties of perovskite crystals, engineers have not just pushed the envelope, they have torn it open. So how did materials science bypass a fundamental bottleneck of physics? To understand the magnitude of this breakthrough, we first have to understand the invisible barrier that has governed solar cell research since 1961. It is called the Shockley-Queisser limit, formulated by physicists William Shockley and Hans Joachim Queisser. This limit calculates the maximum theoretical efficiency of a solar cell using a single p-n junction. They discovered that a standard single-junction solar cell is fundamentally limited by the band gap of its semiconductor material. Think of the band gap as the minimum amount of energy required to knock an electron loose and allow it to flow as electricity. When sunlight hits a silicon solar panel, it arrives as a shower of photons, carrying different amounts of energy across the electromagnetic spectrum. Silicon has a band gap of 1.1 electron volts. This creates a Goldilocks problem. If a photon, like those in the infrared spectrum, hits the cell with less than 1.1 electron volts, it passes right through the silicon without generating any electricity at all. It is wasted energy. On the flip side, if a highly energetic photon, like ultraviolet or blue light, hits the cell, it successfully dislodges an electron. However, any energy it carries above that 1.1 electron volt threshold is entirely wasted, dissipating into the panel as heat. Because of these two factors, the wasted low-energy photons and the thermalization of high-energy photons, Shockley and Queisser mathematically proved that a single-junction silicon cell could never convert more than approximately 3.7% of the sun's energy into electricity. In the real world, due to unavoidable losses from electrical resistance, shading from metal contacts and reflection, top-tier commercial silicon panels have hovered around 22 to 25% efficiency, with lab-perfected monocrystalline silicon cells topping out just under 28%. We have spent decades squeezing every last drop of efficiency out of silicon. To go further, scientists realized they needed a second net to catch the light that silicon was wasting. Enter the magic crystal, the perovskite revolution. Perovskite is not a specific element, but rather a family of materials that share a specific crystalline lattice structure. It is the exact same structure found in calcium titanate, which was discovered in the Ural Mountains all the way back in 1839 by Gustav Rose and named after Russian mineralogist Lev Perovsky. The basic chemical formula for perovskite is AbX3, where A and B are cations of different sizes, and X is an anion that bonds to both. Fast forward to 2009. Japanese researcher Tsutomu Miyasaka discovered that certain synthetic metal halide perovskites were exceptionally good at absorbing light. What followed was the fastest technological advancement in the history of photovoltaics. In less than 15 years, the efficiency of single-junction perovskite solar cells skyrocketed from a meager 3.8% to over 26%. But why are perovskites considered a magic material? First, unlike silicon, which is rigidly stuck at a 1.1 electron-volt band gap, the band gap of perovskites is tunable. By tweaking their chemical composition, researchers can engineer them to perfectly absorb the high-energy blue and green light that silicon wastes. Second, they have incredible absorption capabilities. Perovskites are highly efficient direct bandgap semiconductors. A perovskite layer less than 1 micrometer thick can absorb the exact same amount of sunlight as a thick silicon wafer. Third, they offer remarkably low-cost manufacturing. Silicon requires massive, energy-intensive furnaces to grow pure ingots at over 1400 degrees Celsius. Synthetic perovskites, on the other hand, can be created using low-temperature chemistry. They can be dissolved in solvents and quite literally printed onto a surface like ink on a newspaper. This makes the manufacturing process immensely cheaper and significantly less carbon-intensive. But despite these miraculous properties, early perovskites had a fatal flaw. They degraded rapidly when exposed to moisture, heat, or ultraviolet light, essentially turning back into yellow, non-conductive lead iodide. The ultimate challenge for the last decade was stabilizing this crystal. But once researchers began successfully passivating these defects, the ultimate supercell was born, the Tandem. A tandem solar cell does not replace silicon, it upgrades it. By layering a specialized perovskite solar cell directly on top of a traditional silicon solar cell, engineers create a two-tiered optical trap. Because perovskite is semi-transparent and its band gap can be tuned to around 1.7 electron volts, it is placed on the front line to directly face the sun. This perovskite top cell happily devours the high-energy blue and ultraviolet photons, converting them into electricity at a much higher voltage than silicon ever could. Meanwhile, the lower-energy red and infrared photons pass straight through the perovskite layer, completely unhindered, and are absorbed by the silicon bottom cell. This division of labor is how you bypass the Shockley-Queisser limit. By splitting the solar spectrum into two distinct bands and assigning a dedicated semiconductor to each, the theoretical maximum efficiency of a two-terminal perovskite-silicon tandem cell jumps from 33.7% to a staggering 43%. The journey to actually surpassing the 34% efficiency mark has been a fiercely contested race among elite global research institutions and Tier 1 solar manufacturers. By the end of 2023, the industry was already knocking on the door of the silicon limit. In November 2023, the research and development team at LONGi achieved a tandem efficiency of 33.9%, effectively tying the theoretical maximum of standalone silicon. But the momentum did not stop there. In June 2024, LONGi pushed the record to 34.6%. Other major players like Jinko Solar reported tandem cells reaching 34.76%, which were confirmed by testing centers in China. The defining milestone came in early 2025 when LONGi independently developed a two-terminal crystalline silicon perovskite tandem solar cell that achieved a certified power conversion efficiency of 34.85% at the NREL. Reaching these numbers required overcoming immense nanoscale engineering challenges. One of the primary hurdles was the physical mating of the two materials. You see, modern silicon solar cells are not perfectly flat. Their surfaces are etched with microscopic pyramids. This texturization acts as an optical trap, forcing photons to bounce back and forth between the microscopic peaks and valleys, which increases overall absorption. However, trying to spin coat or deposit an ultra-thin uniform layer of liquid perovskite over a spiky pyramidal mountain range of silicon is notoriously difficult. If the perovskite pools in the valleys and leaves the peaks exposed, the cell simply shorts out. To solve this, researchers utilized incredibly advanced deposition techniques. For instance, a joint effort by the King Abdullah University of Science and Technology and the Fraunhofer Institute for Solar Energy Systems unlocked record-breaking efficiencies on textured silicon by using specific molecules like 1,3-diaminopropane dihydroiodide to passivate the uneven perovskite surface. This chemical treatment healed the microscopic defects at the interface, significantly reducing electron-hole recombination and increasing the open circuit voltage to over 2.01 volts. Another critical advancement was the development of robust charge transport layers. In a tandem cell, Electrons and holes must move seamlessly between the perovskite and the silicon without losing energy. Research showed that utilizing sacrificial interface layers, such as PEDOT, PSS, alongside copper-doped nickel oxide hole transport layers drastically improves the electrical contact, achieving a fill factor exceeding 81%. But a lab record of 34.85% is just a triumph of physics. Lab cells are often the size of a postage stamp, typically around 1 square centimeter. The true test of any solar technology is whether it can be scaled up to full-sized, commercially viable modules without suffering a massive drop in efficiency. This is where the industry's shift from academic research to gigawatt-scale manufacturing becomes the focal point. Oxford PV, a spin-out from the University of Oxford and a pioneer in tandem cell commercialization, has been leading the charge in bringing this technology to the masses. In June 2024, Oxford PV debuted a residential-sized tandem solar module with an unprecedented, independently certified efficiency of 26.9%. While 26.9% is obviously lower than the 34.85% lab record, it is a monumental leap for a commercial-sized module. Traditional commercial silicon panels average around 20 to 22%. Oxford PV's breakthrough 60-cell double-glass module has a designated area of just over 1.6 square meters and weighs under 25 kilograms, making it a perfect drop-in replacement for standard residential rooftop installations. To manufacture these next-generation panels, Oxford PV established the world's first volume manufacturing line for perovskite on silicon tandem cells in Brandenburg, Enderhavel, Germany. Operating on a 100-megawatt capacity line, the facility bridges the critical gap between lab innovation and industrial-scale rollout, utilizing proprietary perovskite deposition tools combined with high-efficiency silicon heterojunction bottom cells. The economic implications of a 26.9% commercial module are profound. According to Oxford PV, commercial and utility customers will benefit from upwards of 20% more power generation from the exact same footprint. This massive increase in power density is the silver bullet for the urban energy transition. Think about it. In densely populated cities, the biggest barrier to rooftop solar is not the cost of the panels, it is the lack of physical space. Most urban homes, apartment blocks, and small businesses have heavily constrained roof areas. Traditional silicon panels often cannot generate enough electricity in a small physical footprint to offset a significant portion of a building's energy consumption, leading to much longer payback periods. Tandem perovskites fundamentally alter this entire mathematical equation. By generating significantly more power per square meter, tandem arrays allow homeowners to maximize their roofs. A roof that previously could only fit a 4-kilowatt silicon array can now host a nearly 5-kilowatt tandem array. That extra power might be exactly what is needed to charge an electric vehicle or run a heat pump straight through the winter. Furthermore, because a large portion of a solar installation's cost comes from the balance of system components, like the racking hardware, the copper wiring, the manual labor, and the inverters, using fewer but highly efficient panels drastically reduces the overall levelized cost of energy. Now you might be wondering, if perovskites are so highly efficient and cheap to make, why aren't they already on every single roof in the world right now? The answer lies in the harsh realities of the outdoor environment. When researchers talk about solar cell stability, they are addressing a myriad of degradation mechanisms. As mentioned earlier, perovskites are highly sensitive to moisture. Water molecules can easily penetrate the crystal lattice and cause it to dissolve. Furthermore, when exposed to high heat and intense UV radiation, the chemical bonds in hybrid organic-inorganic perovskites can break down, leading to the outgassing of volatile components like methylammonium. To gain the trust of the utility sector and bankability from massive financial institutions, solar panels must be able to survive outdoors for 25 to 30 years. This requires passing rigorous International Electrotechnical Commission standard tests, such as IEC 61215, which subject modules to thousands of hours of damp heat, rapid thermal cycling, and intense UV soaking. Thankfully, recent breakthroughs have proven that perovskites can indeed be tamed. Companies like GCL and Utmo Light in China have reported passing stringent IEC testing for their perovskite modules. By encapsulating the cells in highly impermeable advanced polymers and edge sealants, engineers can physically lock moisture out completely, internally, substituting volatile organic molecules in the perovskite structure with more stable inorganic elements, like cesium and formamidinium, has vastly improved the thermal resilience of the crystal itself. Furthermore, advanced surface defect passivation, which involves chemically capping the unbonded elements at the edges of the perovskite crystals, prevents degradation from even starting in the first place. Testing under ISO's protocols has shown stabilized perovskite solar cells operating for over 4,000 hours under continuous indoor illumination and extrapolating to beyond 20,000 hours in outdoor testing environments. The era of fragile perovskites is ending, and the era of bankable, warranted tandem panels is officially beginning. The advent of the 34% tandem cell is not just a scientific curiosity either. It is a major geopolitical pivot point. Currently, the global solar supply chain is heavily centralized, with the vast majority of polysilicon refining, wafer slicing, and cell manufacturing concentrated in Asia. Because perovskites can be synthesized from abundant cheap precursors like iodine, lead, and simple organic salts, all without the need for multi-billion-dollar silicon smelting infrastructure, they offer an unprecedented opportunity for localized energy manufacturing. Europe and the United States are aggressively funding perovskite research right now to build domestic solar manufacturing bases. Oxford PV's backing from the Brandenburg state government, with a $10 million injection, highlights the strategic European push to reclaim a stake in the global photovoltaic market. Similarly, facilities in the United States and the UK are being scoped out for rapid expansion, leveraging the low capital expenditure required to set up a perovskite printing facility compared to a massive traditional silicon foundry. The breach of the 34% barrier is an absolute watershed moment for humanity, but the physics of perovskites suggest we are still just clearing our throats. The 43% theoretical limit for two-terminal silicon perovskite tandems leaves plenty of runway for the next decade of research. But researchers are already asking, why stop at 2 layers? Materials scientists are actively exploring triple-junction solar cells right now. By stacking a wide bandgap perovskite, a medium bandgap perovskite, and a narrow bandgap silicon bottom cell, the theoretical efficiency limit leaps beyond 50%. Furthermore, research is rapidly accelerating into all perovskite tandems. By stacking 2 distinct layers of perovskite, one tuned perfectly for blue light and one tuned perfectly for red, and completely eliminating the rigid silicon bottom layer entirely, manufacturers could produce highly efficient, flexible, lightweight solar foils. These could be manufactured on massive roll-to-roll printers, operating exactly like printing currency or newspapers. Imagine all perovskite tandems wrapped around the curved bodies of electric vehicles, seamlessly integrated into the fabric of tents and backpacks, or applied as a film to the towering glass facades of modern skyscrapers. For decades, the Shockley-Queisser limit was viewed as an immovable law of nature, essentially a strict mathematical budget on how much power humanity could realistically extract from the sun. The 34.85% efficiency record achieved by tandem perovskites represents humanity successfully renegotiating that budget. We are currently witnessing the real-time technological maturation of a true miracle material. What began as a delicate crystal that simply dissolved in humid air has been engineered into an absolute industrial powerhouse, capable of augmenting silicon, doubling our power density, and drastically accelerating the decarbonization of the global electrical grid. As gigawatt-scale factories spool up their production lines and residential modules exceeding 26% efficiency begin hitting the market in scale, the entire narrative of solar power shifts. It is no longer a story solely about finding vast tracts of empty land to build sprawling arrays. It is about hyper-efficiency. It is about turning every sunlit rooftop, window, and surface into a high-octane generator. By breaching the 34% barrier, perovskite tandem solar cells have proved that the future of clean energy is not just brighter, it is infinitely more powerful. Thanks for tuning in to G Fun Facts Online, and keep wondering.